Hess's Law is up next, and what this concept really is used for is to calculate unknown enthalpy changes for reactions. So we may have a chemical reaction and it'll say, what is the delta H for this chemical reaction? We would use Hess's Law to calculate that. Now, it can be done in two ways or two different methods. They're both considered Hess's Law, but one way is a little bit longer than the other. And so I've kind of dubbed them, this is not an official term, but I've kind of dubbed them Hess's Law the long way and Hess's Law the short way. So I'm going to go through both of these methods so that you know how to calculate delta H's for reactions that are unknown, or delta H's that are unknown, and go through both of these methods so that you have them. You do need to be able to do both of these methods, and you will see questions that will test your knowledge on both. Hess's Law the long way is first. So you can see we've got a chemical reaction up top, and it's asking us what is the delta H for this reaction. Now, everything that you see here on the board in blue ink is what is going to be given to you in the question. So you'll be given a chemical reaction with the unknown enthalpy change, and then you'll be given a bunch of smaller reactions that look smaller anyways, that are smaller, with their delta H's as well. Now, these just happen to all be formation reactions, so I've written them as delta FH just to indicate that they are formation reactions, but nonetheless, all of this stuff would be given to you in the question to do a Hess's Law the long way question. Now, an analogous example that I like to give kids to kind of introduce them to this is sometimes if you've ever done one of those like 1,000-piece puzzles, or lots of people sometimes, I guess, do these puzzles at Christmas time, they lay them out on a big table. Anytime you've done a puzzle, most likely what you've done is you've kind of taken the box that the puzzle comes in, and it's got a picture of what the puzzle looks like, and you set that box up so that you can refer to the picture on the box while you build the puzzle. And so the analogy I like to draw from that to this example here is that this reaction right here is the picture on the box. This is what we have to try and rebuild using these smaller puzzle pieces here. And we can rearrange them just like you would do with a regular puzzle piece, so that the stuff that we have here is identical to the stuff that we have up here. And as we rearrange, we have to do certain things with the delta H's that I'll illustrate here in just a minute. But the goal here is to, using these three puzzle pieces, rebuild this chemical reaction. And then once we do that, we can take the addition of all of these delta H's from these small reactions that we used to calculate what our delta H is going to be for the main reaction that we just rebuilt. So what I like to do is I like to just go reaction by reaction to make sure that it's arranged properly. And so you can see that this reaction that I'm trying to rebuild has methane on the reactant side. This puzzle piece here, this mini reaction, this formation reaction, has methane in it, but it's on the wrong side of the arrow. It's on the product side. So what I'm going to do with this is I'm just going to flip this reaction so that it's written as a decomposition reaction, not a formation reaction. That puts methane on the reactant side. And so you can just erase this. And write it out the way that it's supposed to be. On a test, you wouldn't be able to erase the ink on the paper, but on a scrap piece of paper, you just would redo this so that it's set up the right way. Now, because this is now a decomposition reaction, not a formation reaction, that means that this reaction is no longer exothermic, it's now endothermic. And so I just changed the sign for that chemical reaction to be 74.6 kilojoules. So now that I've got this on the correct side and there's nothing else in here that really is found up in this reaction, I just leave the rest of everything else that's there. That'll take care of itself at the end, as you'll see. And I move on to reaction number 2. So reaction 2 here shows that I have carbon dioxide on the product side, and this reaction here also has carbon dioxide on the product side. Now, something else that I want to check for is I want to check to make sure that the coefficients match as well. You can see here I've got 1 methane in this reaction, and I only have 1 methane in the reaction that I'm trying to rebuild. So that matches, and that's good. Same thing with the carbon dioxide here. That matches this and this. So for this one here, I don't need to do anything for that. I can leave it as is, and that delta H is good, negative 393.5 kilojoules. I don't need to, if I don't change anything in this reaction, I don't need to change anything with the delta H. Reaction 3, though, does show what else can kind of happen with these reactions. Now, we can see, again, we've got water vapor on the product side, and that's good. I do have water vapor on the product side in the reaction I'm trying to rebuild. But you'll notice that this has a coefficient of 2, and this one only has a coefficient of 1. So what I'm going to do to this reaction is I'm going to multiply the whole reaction by 2 so that I can get a coefficient here of 2. So I times that by 2. 2 times 1/2 is just 1, and then 2 times 1 is 2. Now, when I multiply this reaction by 2, I have to also show, okay, if I'm going to have twice as much happening here, then I'm going to get twice as much heat being released as well. So I have to multiply this reaction by 2. That gives me a negative 483.6. Okay, now once I've done that and I've rearranged all of my puzzle pieces, as I like to call them, so that they match up what is found in this reaction up here, now I got to make sure that everything that's extra cancels out. And if I've done the rearranging of these reactions properly, everything that is in these 3 smaller reactions that isn't found up here should cancel out. And by cancel out, I mean we've got the same amount on the reactant side as we do on the product side, and so they're canceled out because of that. And so I just kind of draw a line like this to show that I'm just going to add up everything here. You can see that I've got 1 mole of carbon on the reactant side and 1 mole of carbon on the product side, so those will cancel. You can also see that I've got 2 moles of hydrogen on the reactant and product side, so those cancel, and those are out. And everything that's left over should be found up here in this reaction. If I have something that's left over that isn't found up here, I know I've done something wrong. So that's a bit of a safety net where you can kind of catch yourself making some mistakes and go back and revisit what you did and see if you can identify where you went wrong. Here, it looks like I've done everything right. I'm just going to go ahead and write down what I've got. I've got 1 methane on the reactant side. I've got 2 oxygens on the reactant side. Now, because both oxygens are on the reactant side, those add up, they don't cancel out. And so I just write 2O2 like that. You can see that I've got 1 carbon dioxide on the product side and 2 water vapors on the product side. So I'll write those out as well. And you can see that by using these 3 reactions here, I've been able to perfectly rebuild this reaction that we started with up here at the top. And now, to solve for this right here, all I have to do is I just have to add those numbers up together. The biggest thing that you got to watch out for is integers, positives and negatives. If you punch this into your calculator correctly, what you should get is a negative 802.5 kilojoules. And so the heat of reaction for the combustion of methane is a negative 802.5 kilojoules. So Hess's law the short way really has basically the same end result as Hess's law the long way. It just is a slightly different path or way that you get to that final answer. What I'm going to do is I'm going to illustrate to you Hess's law the short way by using the exact same reaction that we used in the previous example so that you can see that we arrive at the same answer even though we do it in 2 different methods or 2 different ways. And so if you remember from the previous clip, our answer that we should get is negative 802.5 kilojoules. So that's what we're going to look for as we do this. When you're doing Hess's Law the short way, or how you identify, hey, this is a question where I need to do Hess's Law the short way, is again, you've been given a chemical reaction here, and it's asking you to calculate what's the heat of reaction for that chemical reaction, but it doesn't give you any puzzle pieces here. There's no smaller reactions to rearrange or anything like that. All right, and so the formula that we use for this type of method is this one right here. And all this says is that the heat of reaction can be calculated, or is equal to, the sum of all of the heats of formation of the products minus the sum of all the heats of formation of the reactants. Now, a couple of things to point out with this. First of all, you're going to need to make sure that you are doing the sum of these guys first, and then the sum of these guys second. Before you do the subtraction portion of it, you need to make sure that you do the subtraction last. All right. The other thing to make sure that you're doing is that you are doing the sum of the heats of formation of the products first. That goes at the front of the subtraction that you need to do. And then the heats of formation of the sum of the heats of formation of the reactants goes at the end. And then the last thing to make sure that you're keeping straight is that you can only do Hess's Law the short way if you have heats of formations of each of the substances within the chemical reaction. If you do not have heats of formations for those, you cannot do this method, and likely there's other reactions that have been given to you where they're trying to get you to do Hess's Law the long way. So this is what you need to watch out for as you're sort of identifying when am I going to use this. So if I go to my data booklet, what you'll notice inside of your data booklet is on page 4 and 5, you'll see this chart here. And if you look at the top and read the top part of the chart, it says that those are standard molar enthalpies of formation. And so for any substance that is found in that book, you can use it for solving these kinds of problems. Now, if you look in the book, you can find methane, carbon dioxide, and water vapor all in that book, and they all have their heats of formation there. So this makes this question quite simple. This is how I like to do it. I like to go into the book and I like to look up, okay, what's my heat of formation of each one of these substances, and I just like to write them down below. And so in the book, because it says it's a standard molar enthalpy of formation, it's in units of kilojoules per mole. And so I have to pay attention to the coefficients found in front of each one of these substances in this chemical reaction to make sure that I'm accounting for how many moles I have in the balanced reaction. For this one, I have 1 mole of methane, and I know, looking in the booklet, that the molar enthalpy of formation of methane is a negative 74.6 kilojoules per mole. Now, because I only have 1 mole of methane here, then I know that that's just set negative 74.6 kilojoules. And so writing the moles becomes no longer redundant. It's like I've multiplied this number by 1 mole to cancel out the moles. The molar enthalpy of formation for an element is 0, and it's because elements just have existed since the beginning of time. And so we don't form elements, they're just there. And so because of that, they don't have a heat of formation. And so it's just 0 kilojoules for any elements that you find in a chemical reaction. For carbon dioxide, I look in my data booklet again, and that's negative 393.5. Now in the data booklet, it is kilojoules per mole, and because in this chemical reaction I only have 1 mole of carbon dioxide, then if I just multiply this number by 1, that cancels out the moles, and it's just negative 393.5 kilojoules for carbon dioxide. Water vapor, if I look, is a negative 241.8 kilojoules per mole. And because I have 2 moles of water vapor in this chemical reaction, then I need to times that number by 2 moles. And if I times it by 2 moles, then the moles cancel again, but it's also going to change the number to a negative 483.6. And so there's my numbers. Now, what I need to do is just take my calculator And I'm going to take the sum of the heats of formation of the products first. And so I add those numbers up together. And that gives me a negative 877.1. And then I take the sum of the heats of formation of the reactants, which is just negative 74.6 kilojoules plus 0, so negative 74.6. And again, you can see why we need to do the subtraction last, because now we've got the subtract a negative. I plug that into my calculator, and if you plug it all in, again, you should get a negative 802.5 kilojoules. And that's how you do Hess's Law the short way, guys. Hopefully this was helpful. Good luck as you attempt some of the practice questions.